All right, so after this lecture, we're gonna have the next lecture on Monday. We'll start talking about the backpropagation algorithm. After that, you're gonna be having your second assignment, which will be 99% implementing a backprop from scratch in Python in TensorFlow. I'll give you the instructions afterwards. So, but just to let you know that next week or this weekend, I'll post the next assignment. All right. So, yep.
So the midterm is up to lecture 10, right?
Yes. So midterm would be up to last week, previous week actually, before the reading week. All right. So let's talk about our discussion about neural networks. You recall in the previous lecture when we talked about the first part of neural net, we talked about the simple case of having a two-layer network and a binary classification. Okay. So we talked about the fact that we can feed those inputs that are shown as x here, x0 as the artificial coordinate of 1 up to the xd, and then you're going to have some weights allocated to each of those, and then you have one activation layer. So these are your hidden layer here. So that's the input, that's the hidden layer, and that's the output. So here and there, we were talking about integrating some nonlinear functions. We call it phi or theta, depending on the algorithm and the type of the model we were using, and that would be the output of us. Okay. So about the formalization, we talk about this notion of Wi and j, which corresponds to weight on input vector of I to the hidden vector of j. Okay. So just like this. So for instance, Wi2 would be the vector of input of 1 towards the second one. So this would be W12. Okay. And we carry on. Let's see here. Pointer. And we carried on defining the hidden layer of j, which we call h of j, as the output of the activation function theta, which is based on the w's of coming from the previous layer, right, and its own. So actually, we integrated this into itself. So so that was actually the bias weight, not the previous layer. That was the bias weight. So we integrated it all together and showed it in a vector format. So this is a vector notion of all the w's. Actually, this should be 0 here, including the bias term. So all the w's from 0 up to n. Okay. And we talked about the output. If you want to formulate the output, it's going to be the activation again at this point. So this is the activation here we're talking about. Which is the W, the V0 or mu0 plus the summation of all the Vj's Hi's. So this is coming from the hidden layer in the previous layer, right? So we talked about that in neural network, this nonlinear function is called hyperbolic tangent. There are so many other variations of using a nonlinear activation. And we talked about the differences between a sigmoid and a hyperbolic tangent, which you used to see in your logistic regression with respect to neural net. And we talked about the superiority of hyperbolic tangent. First of all, it's going to encompass all the values as the output from -1 to 1. So the gradients are higher around zeros. In general, experimental results show that it's going to have a better convergence rate when you couple that with stochastic gradient descent. And because of this, normally we prefer hyperbolic tangent over sigmoid function in neural nets. So let's talk about the rest of the story about neural nets. And the starting point would be this paper which was later known as universal approximation theorem. So two set of researchers at the same time. So I mentioned one of the papers here, 1989. There was also another group that came up with this notion at the same year, 1989. And basically, this universal approximation theorem states that with a 3-layer neural net with sufficiently many hidden units, so if you put sufficient hidden units inside a 3-layer neural net, you can virtually approximate any smooth decision boundary. So so in statistics, normally we talk about decision boundary as a hypersurface that partitions underlying vectors, right? So say you have, this is your space, say you have these minuses, right? This is a smooth decision boundary, right? This is a non-smooth decision boundary. There are so many definitions with that, but as a very simplified version, just accept it as this as a smooth decision boundary as a hypersurface. So if we go to higher dimensions, we're going to have a hypersurface that partitions the underlying vector space into two sets in the case of binary case, right? So basically, this theorem states that no matter what function we are trying to learn, we can try to imitate or approximate the learning factor using a sufficiently large MLP, right, with certain amount of error. That's why we talk about approximation here, because in general in machine learning there's no closed form solution. There is no absolute generalized output, right, as the final solution. It's not a linear algebra, right? We are trying to approximate, we are trying to minimize the error as much as possible using various techniques. So let me just get rid of this here. So just like what you knew before, with at least 3 layers and sufficiently enough of hidden units inside that, we can approximate any decision boundary. So we can do a classification task for at least a binary decision. And so this laid the ground for many other researchers that started to work on neural networks and expanding on many other domains that you see the applications by now. However, within this paradigm, there are two different things to tackle. First, we tackle the first one, which is how we're going to come up to this y here when we feed something as input. How we're going to traverse through this network to come up with the y, okay? And the next big question, which would be the hardest one, or the harder one, is when we reach this point and when we check the output of our neural net with the real, actual, true label, how are we going to fine-tune this and back-propagate all those differences in the weights coming back to the network, right? So that's a harder task. The first task that we're going to talk about today is going to be feed forward, because we feed from the we feed the inputs from the left side and we go all the way to the right side, right? We call this feed forward. And then when we reach this and we compared it, right? Let's say this is a comparison with the true label or true value in regression, right? And we found the differences. How are we going to affect all those internal units all the way to the first W, right? So we call this backward propagation, BP. All right, so let's start talking about the feed forward pass or the forward pass in this lecture. Okay, does that make sense? All right. Also, forward pass is also known as training, right? Because you are trying to pass inputs to your model to train it. And then using the backprop, you're trying to update those weights to converge faster, right? So let's see how the training process works here. So in general, if you want to try, if we try to define the notions here, so we can call the input layer the first one. So say if we have L layers from 0 to L, capital L, L equal to 0 is the input layer, right? All the hidden layers in between those to the output is going to be those L's from 1 up to L, and the output layer would be the capital L, okay? So that's the notion of the layers, layer numbers. As you already know, affecting this to the previous definition of Wij, so we're going to have Wij for the specific layer of L that we can show it like this. So the weight connecting nodes I in the layer L minus 1 to the node J in layer L, right? So this is the layer L, this is the layer L minus 1, so the previous layer. So all the nodes coming in with their specific weights, we can define it as Wi and J of L. Just like for that, we can define the number of nodes in that specific layer, right? Excluding the biases with D of L here. Okay, so if we sketch a very high level scheme of a neural net, you're gonna have this. So in layer L minus 1, so say you are somewhere in the middle of a neural net, so you're gonna have, this is your current layer, layer L, this is your previous layer, right? And this is the output of the current layer to the next level, L plus 1, right? So all the weights are coming here, W0 and J of L, W1 and J of L, up to WD and J of L minus, so actually these are all my L minus 1. WD and J of L minus 1, okay? They're coming here. So you are trying to activate it in a way that your neural net has been designed with that specific activation function, right? Then you're gonna pass it to the next level as the output of the activation, right? This is the output of your activation. Sometimes we call these weights activations because this was the result of the output of an activation function. So we call these weights of a model, and we call these the activations of the model. Sometimes we refer to these two with these names. And then you pass it to the next level, so you can have those J from J and 1 up to J and D of the L plus 1. Okay? So just like that, we can define an input in node J of layer L as Sj of L, right? That's what you see here. And the output, let me just get rid of this. All right. So if you wanna expand on Sj of L, it's going to be equal to the bias term W0 and J of L plus the summation of all the weights from I to D L plus 1, right? All those Wi and J of L multiply their input, right? So this with this, okay? So you multiply this with this, and all the different combinations if they are available, okay? So far so good? All right, so let's see a vector notation of the following scheme. So instead of defining those S as this, as a summation of all those weights, right? I can define it in a vector format as a vector of S in a specific layer of L, and each of those has S1 of L, S2 of L, up to SD of L, okay? The activations of S, the output of that, right, is going to be the theta of S of L. So this is the output of the activation function. So you can expand it on just like that with the theta of S of S1 of L up to theta of S of D of L, right? So that's the last node in that specific layer. That was the first node. Here, E. And just like that, you have the vector of X. The first one is the bias term. It's going to be 1, right? And then the rest would be the output of the activation of, again, theta of S of L, okay? Likewise, we can define the W, the vector of W, in the specific layer of L as the W of I and J of L, and we define the I's from 0 to D, D of L minus 1, right? These are for the previous layers. And J's are from 1 up to DL, okay? And then don't get scared. This is the output, right? So the vector of L would be corresponding to a matrix such as following. W0 and 1 of L. On this side, you have from 0 to D of L. So here would be this side. And here would be from WD L minus 1 of L up to WD L minus 1 D of L. Okay? So that's why all of those are inside the R space of DL minus 1 plus 1 multiply D of L. Okay? Is that clear?
Can you have an example of like small neural two neurons and 2 layers so that we can understand?
Sure. I guess I have provided you some examples here. Yeah, I'll provide you. No worries. Yeah. Any questions? So now, coming back to your question, if you have only 3 layers, right, you're gonna end up something like this, or even better, here. So say that was your first layer, second, that was your third one, okay? So here, all the W's, so in order to compute the input for the activation, what you're gonna do is you multiply all the W's to the inputs, right, the corresponding inputs, and you sum them up, okay? And then you come back here, you apply the activation, so that would be the activation function of all those coming here to the S of J, and S of J was the matrix as the output of the multiplication of this, right? That's why in neural net, in computer systems and computer architecture, is very, so these multiplications and additions are called, I forgot the name, MAC, number of MACs, right? So you define a network, the complexity of the network with the number of MACs, the number of multiplication and number of addition within that network. So that's the actual computation that you need to perform in order to come up with either the feed-forward pass or the backward pass in each of those training iterations, okay? And this is the costly computation within neural nets and convolutional neural network and RNNs and so on and so forth. The more you expand your network, the higher the number of max would be, because you have so many multiplication and additions to perform in order to just get your output. All right. So for the vector notion, the notation would be the jth column of WL is going to be corresponding to the weight incident on node J in layer L. Okay. So S of L would be the transpose of the vector of W's, right? Multiply to the vector of X's. Just like what you had before in your credit card application, right? This is your WT by X, okay? All right. So if you follow the feed-forward path, you're gonna start from the x's, x of 0, which was the first coordinate, x0, up to x of L minus 1, right? You have the w's corresponding to that, and then you're gonna compute the s's, s from 1 up to L. Then you activate those s's using your activation function. This is a function. And then you're going to come back to the next level, right? So now this would become the next set of inputs for the next layer, right? And you just have another set of these here, actually from there, right? In each layer. So what you have is your space would be a D plus 1, right? With all those D's here. You have the W's, you compute the S, you activate them, and then you pass them to the next level. Okay? You got the overall flow? I'll wait here for a second so you can have a look at it. Yep.
Are there cases where you combine, like at the end, you have less number of x's for your next layer?
Yes. Normally these are not in neural nets, the pure neural nets. Are you talking about the output?
Yeah.
So the output, yeah. If you have a binary classification, definitely you need to have a binary output, right? If you are, it depends on your output function, right? If you are trying to classify a binary case, so definitely you need to have one output. If you are going for a multi-class, you need a softmax before that to just outputs depending on the output classes, right?
Is that when you output, or it happen in some of the hidden layers?
So normally softmax level, it's happening one level before the final output. So depending on, so in image classification, for instance, in ImageNet, right, when we have 1,000 plus one dummy class, so that your softmax function would output 1,001, right? The first one would be cats, dogs, and so on and so forth. If you are trying to, for a credit score, a very simple application, if you want to approve or reject somebody, it's going to be only one, right?
How about for regression?
How about for what?
Regression, if you want to predict something, like, then what would be the...
You can still use softmax.
But like, if you want to predict the price of a house based on the features, so it would be software would give the probability.
Um,
Then it would be class.
yeah, I mean, it wouldn't be the same. You need to tweak it a little bit. Yeah, but the case you're seeing for now is mostly classification using neural net. Okay. Also in CNN, coming back to your question, in CNN where you have, because in neural nets normally you have, we call these fully connected layers, because for each of the layers normally you have all of those. So say you have if you have 3 layers, you have 3 and 2 here, okay? So we call this a fully connected layer because all of those are connected, right? And then it's going to go again up to here, right? Fully connected FC. Sometimes in CNN, which is another class of machine learning, deep neural net, you don't have a fully connected layers. You have a convolutional layers, right? A conv layer. So they are working differently. We're going to touch on that on their own respective lecture, okay? So not necessarily all of those should be. All right. So let's talk about the forward pass that I was mentioning some minutes ago. So the forward pass is the process that we start feeding the network from the input, go all the way up to the output, okay? So this is called a forward pass. Let's see how we're going to define it. The inputs would be your input vector, your x of 0, right? The first layer. It's going to start from this bias term and x1 up to xt. So we have d-dimensional space here. For number of layers from 1 up to the last layer, so as a capital L, you have to iterate and keep computing the S of L, right, which was the output of the multiplication of your W transpose and your X, which was the input of the previous layer, right? So if you want to compute this and you activate it, the coming weights and those X's previously, right? This is the way you compute your S of the layer L. Then you're gonna have your XL, which is the output. These are the activations, right? As 1 and the output of the activation theta of S of L. Is it clear? So you see all the buzz about neural net and deep learning is just a a number of max. Finally, it all comes down to some max. So you multiply and you add and you activate. That's all.
So the output of layer L, how many dimensions will that be? Is it arbitrary? Like you can select how many?
It depends on the way we design a model. So for the case of XOR, which I was showing in the previous lecture, so you needed like 2 perceptron, and depending on the number of regions you want to try to classify, you have different things, yeah. But it gives you the power to expand and then just All right. So let's see the computational complexity of a forward path. So you can easily see from the high-level model that I showed you that the total number of nodes, right, you're going to have from D0 up to DL in each of the layers, right? We have D nodes in the input layer. We have D nodes, the first layer up to D nodes, if we are talking about the fully connected layer, right? We have D nodes. We call it by V in the graph notion. So you have V and also edges. So the total number of edges, all those arrows that connects these two, we call it by Q. It would be the summation of all those layers. So from layer 1 up to L minus 1, because L is the last layer. So you're going to have, if you recall, you had two different dimensions, right? You had D plus 1, D of L plus 1, which was the Bayes term, and D of L plus 1. Okay? So let me just come back here. Here, you see? That's the size of all the edges for each of those layers, and then you have to sum them up over all the layers that you have. Okay? So we can compute the Q's easily by just summing them up and multiply d of L plus 1 to d of L plus 1. Okay? So the total number of computations, since normally in modern neural nets, this is way larger than the number of nodes, we refer to the total number of computations as an approximation to only Q's itself. Okay? All right. So now we know how to compute the output of the forward paths. Now we know how what are the computational complexity of such a forward path. Let's see how we're going to deal with the output and how we're going to compute the loss function from the output that we had. Okay, just like before, for the loss function that we defined, which is the output of our g function of x of L, which is the output of the activations in the final layer, which is the predicted actually value, right? We use again square error, right? So x of L minus y square. In the case of regression, we were using square error, right? In the case of classification, we were using log loss, just like what we did in the logistic regression, the binary classification. Okay. So we can define a set of model parameters. We call it a big omega, which contains all the W's that we need to find, right? So these are all the W's of each corresponding layer in a neural network that we have to learn, right? So these are our model parameters. So we can define the pointwise loss function given our model parameters as the equivalent of loss function applied to example xn and y. So each example in a pointwise loss has its own loss function. So using that, we need to find a way to adjust our weight and come up with a new set of weight, right, through our model parameter, and to converge by training more and more, right? Let's just plug this notion to our stochastic gradient descent that we talked about some lectures ago. So saying in iteration number k, we select one input data, right, at random, x of n with its own y of n. And suppose omega k represents our parameter at that specific time in the model. So that neural net had its own set of weights. So this was the weight 0, weight W1 up to WL. So these were our parameters in this set, right? So we have to apply a forward pass to compute this E of n given our current weight, right? Because at the end of the day, this will output x of L for us, and we compare it to the true value, right? We can compute this E of n for that specific training example. And then, in order to come up with the gradients, right? Because we are trying to go downhill using the stochastic gradient descent in our loss function figure, right? we start with a higher loss. So this is the number of iterations. So the more we go higher, we want to try to minimize the loss, right? And we mentioned in 3D that it's going to be something like a paraboloid. So we start from either of these, and we want to go down. So we need to find the gradients with a step size to show us where to go, right? So the gradients would be, you have to compute the partial En of omega k, so which was all the weights in our model, with respect to all the w's, right? So so these are the parameters that we have to treat them for all the I, j, and l, okay? For all the nodes, edges, and all those layers. So the update would be as follows. We use the gradients. We apply the step size minus, because we're going downhill, that was the previous W, and this would be our new W, right? The updated one. Let's say the update. Updated. Just like before. Yeah.
Like we are finding the gradient for every W, right? For every
Yes.
W for every layer.
Yeah,
So like
yeah.
if we update it for like first year layer, and then we update it for the second node. So it could be possible like the first node will not contribute to the second one, the minimum, and it's
Yeah.
lead to a problem because we are not taking account of everyone.
That's a very good question, and that's the job of a backprop. Yeah, we're gonna talk about it starting from next lecture. Yeah, we need to specifically mention what was the contribution of the delta with respect to all the model going backward. Yeah.
Just a general question about gradient descent. These learning rate, does that get updated each time, or is it a constant?
You can treat it as a hyperparameter. Depending on the type of a stochastic gradient descent you're playing with, is it a vanilla one? Is all those variations that we talked about previously? You can have one fix, or sometimes in TensorFlow or PyTorch or Caffe, in some packages, you can make it adaptive, right? But for now, assume this as a constant here, step size. Any questions?
When would you actually be able to update the weight of that?
In the backward path, we are trying to update the weights.
So is
In the forward path, we just follow through all those multiplication and additions to come up with a loss, right? And we compute the loss. We have to, so we know that there is certain amount of differences to be adjusted, right?
Yeah.
So how we can adjust these small differences throughout the model backward? So that's the backward pass. We're gonna talk about it next lecture. Yeah. All right. So in a high level, it's as if you compute a Wij plus a small delta W, right? We need to compute that for the next layer, next set of training examples. So the job is here now. How are we going to compute a partial E of n of our model parameters, all the weights, omega k, with respect to all those W's, right? If you treat those W's as variable, because at the end of the day, we are trying to train a model. That means we are trying to update the weights. Because if you download the trained model, all you see is like a model which a different set of W's after many iterations. So that's the job. Finally, we are trying to update the model parameters. Okay. So using a stochastic gradient descent in high level, we need to replace those previously found W's and adjust them a little bit with a delta. So a delta W. and keeping all the other weights untyped. Okay? So for the sake of the argument, let's assume you have a omega k plus, which is the new set of updated weights as a result of this update. Okay? So what would that be? It's as if you are, for computing the partial En of omega k divided by partial w's, right? It's as if you're subtracting the previously found weights from the new weights divided by w, delta w, right? Does that make sense here? Can anyone explain why? Going back to algebra, you know the function here, right? You wanted to compute the partial at this point. It was as if you are trying to see how different would be near this w, right? So say small window. That's it. Say this is your En. Can anyone explain?
I think we can find the slope on this.
Yeah, it's sort of an approximation to find the slope, right? Because the slope would be the differences between your y function, if you're having a y and x, with respect to the small changes in x, right? That's why you do a derivation in general. Still not clear?
Like in equation 2, we are updating the wij with delta w, right?
Mm-hmm.
And the delta w is coming from where?
So delta w is the one that we needed to have had we wanted this to be exactly the same as the true output.
So how we will come to know by gradient, right? Like
So we do one forward pass, right? We find our predicted values, right? And we checked it with the true value, right? We found a small differences. That would be delta w, right? That we need to update, okay? How are we going to affect this through a stochastic gradient descent towards going in the right direction now? That would be the job.
So the same delta W is added to all the weights?
It depends now. It depends. Because the weights in the previous layers or in the first layer or one layer in the middle might not have all those contributions to that small error, right? So you have to find a way to adjust it depending on the place they were. Yeah. Yep.
Can you explain again what omega k plus is?
Omega k is just a set of model parameters here. Just think about all the set of your weights in each layer.
K plus?
So k plus is the new set, like when you update your weight. We call it a plus to differentiate between the old and the new one. Like this, this is a new one, this is an old one. Because you updated it, right? Let's call this in the, I don't know, iteration plus one, right? If it's not clear, ask questions. Yeah.
So are we trying to find a way to compute the partial? And so, but are we saying omega k plus is the future? Like it's like the next?
Yeah, we are trying to find a way to update our weights using the loss that we found, right?
So that's why it's like, okay, so this is like the whatever change we'll make minus whatever.
Exactly, yeah. And as you perhaps might have noticed, we have to repeat this for each of those W, I, and J, right?
So that's why we have to do the backwards pass, because you can't start computing any of those like partials until you have the last output right, and then you take it back.
Yeah, so when we complete the forward pass and we apply a gradient descent and we want to make sure how we have to adjust the weights, we have to come up with a plan to adjust, to propagate those adjustments throughout the network,
Yeah.
backward, coming from the last layer, one before the last, and up to the first layer, right? And since you have all those activations, which is a nonlinear function in the middle, you have to find a way to adjust that, right? So that's the job of a backward pass.
So, so we have delta W already, right?
Because we find that if we had this delta W, our predicted value would be the same as a true value on that specific training example,
Right.
right?
So that's a known value then? Delta
Yes.
W? So
Because
then,
it's a supervised learning, you know the labels or you know the actual output, right?
so then, what do you need the derivative or error for if we already know we can update the weights with our delta?
So if we adjust the weight with that, if you had that delta W on that specific example, that specific training set, training example would give us a perfect score, right? But what about the rest? And so
So the one's like localized and
that's
like
right,
global.
yeah. So we were sort of here in a paraboloid, right? We need to find somewhere that works best for all of them, right? So perhaps we're here. We have to find a way to come up going down that steep hill, yeah? And that's the job of a training. Okay? So, in a stochastic gradient descent, because we have to apply this for all of those weights, roughly speaking, the total number of computations would be around q squared, which was the number of edges, right? Square. Thus we can say the complexity per update is going to be in the order of q squared, which is a very, very high order. And that's only for one round of forward and backward pass. In modern neural nets, you have normally at least 10 million edges. So this order for sure wouldn't be acceptable for just one round of training, okay? Training would take a long, long time. And actually that was one of the major obstacles in front of neural nets in the 70s and early 80s. Up until the point that this backpropagation algorithm got much, much more efficient with the order of O of Q. And that was a famous paper of Geoffrey Hinton, who is the professor at the University of Toronto. So he found a way to make this process much more efficient. So instead of order of Q squared, he brought it down to the order of Q. So now the complexity per update is going to be much, much lower. So you can afford to go for like 10,000 times, 20,000 times, 100,000 times to train a model, right? And doesn't take you like 10 years to finish one training. So that was a paper, Learning Internal Representations by Error Propagation, 1986. There are a lot of math there. It's outside the scope of our course, but you can have a look at it if you're interested. So the job would be when we find an output of 1 feet forward, which is x of j of L, right? We need to go back and adjust those W's, delta W's throughout the previous nodes. Okay. Backprop uses a very well-known notion of chain rule. We will talk about it extensively next lecture. But for now, you can just think about it as sort of an expansion. So you can expand the partial En of the omega, which was the model parameter, with respect to W's, as the partial En of omega with respect to S of J, right, the first level, and then you can compute the partial of your first level with respect to W. So we call this a chain rule. You see, we can add these together as a chain. So when you are here, looking back, right, you see all these modules at once. Okay. You can update up to here. This is equal to one update up to here, and then see the rest up to here. Or this is equal to coming from here to here and see the rest from here. Okay. So this is called a chain rule. So you can expand En as En of Sj and Sj of W. And that Sj would be another previous layer, and you can go on, so on and so forth. Okay? Does that make sense? We talk about this extensively in the next lecture. But that's the whole idea. It uses a chain rule to update backward. All right. So let's see what exactly we need to compute in next Monday, actually. So let delta J of L be the exact update that needs to be done backward, okay? So this is equal to the partial of S of J with respect to Wij, right? Let's call this is exactly equal to xi of L minus 1. This was the input of the previous layer. And recall that from the previous lecture, in order to compute a hidden layer Sj, we would have to compute the W's and the inputs of that specific layer. I mean, the weights of that layer and the inputs of the previous layer, right? In a summation. Up until it is clear? So in order to update your partial En with respect to your W's, you actually need to multiply xi of L minus 1, your previous layer's input, to the delta that you found at that specific location. So if you come back, that was your XL, you found the update, right? So we called it delta J of L at the point of L. So this would be equal to, actually, the model's update at this point, which is the partial En of W, it would be equal to this multiply the inputs coming to that from the previous layer. So L minus 1. Let me just show you back this figure here. So that's your predicted output. You find a loss, you find delta W, and you need to compute the partial, you need to compute this, right? This would be equal to this plus the input coming to this from the previous layer. So partial En with respect to W's is equal to xi of the previous layer and a delta that you have here at this specific layer. Okay? So we have to compute this for all the i's and j's. So with the different dimensions d plus 1 and d. In vector notion, it would be just the vector of x's, l minus 1, up multiply the delta of l. So these are the updates, the partial updates. So this vector would be this, x0 l minus 1 up to xd l minus 1, and this vector would be this. So up until this point, we have everything available except that delta itself, right? Because we already had the previous layer's input. How are we going to compute that matrix for each of those, or that vector for each of those specific layers? And that's the job of a backpropagation pass. So you start from the back, so let's see it from, so this is your output, right? Now you find some values, and you want to go backward. That was your input. So this would be equal to partial En of your W's, right here, going backward. This would be equal to the first layer, this error, plus multiply this error, right? So that's the chain rule. So you arrive here, and this would be equal to this error. You arrive here, this error to the rest of the error. And then you just narrate down, going backward up to the first layer. Just go backward. And we talk about it extensively. Okay? But the notion we will use is the chain rule notion. You can expand on this by the hidden layer in between, because at the end of the day, these two are are the same, right? This is still a partial of En by W. We're just expanding on it. Okay, questions? You hate neural nets now? All right, if you don't have any questions, I guess I'll wrap it up now and see you next lecture in the midterm. Have a good day, guys.
So for the midterm, will the questions be primarily based on the questions that you put on Moodle, or will it also include lots of slides?
Yeah, read through the slides. If you have attended the lectures, and read through the slides, and also if you have done your assignment by yourself, and if you have taken some time in order to solve that sample questions, you're gonna be fine. Yeah.
Will you post a solution to the assignment?
Perhaps.
Just so
Okay. I'll talk with your TA and see. Yeah. Okay. I mean, since you had all these MATLAB functions, you could just run them in 2 lines and see the output, right?
But then we wouldn't see how to do it on our own.
Okay. Fair.